Hello friends, welcome to my third lecture on this topic, methods for finding particular integral for second order linear differential equation with constant coefficients. We are trying to find the particular integral for second order non-homogeneous linear differential equations where Rx is of some special forms. So, if Rx is of the form x into b, where b is any function of x, how we shall evaluate the particular integral. So, particular integral in the case when Rx is x into b. So, when you differentiate x into b, what we get is x into db plus b, because b is any function of x. Then d square, when you operate on x into b, you get x d square b plus 2 db. So, since d square is since fd is d square plus say alpha d plus beta, fd, or here I have taken d square plus ad plus b. So, fd x b, fd operating on x into b will give you d square plus ad plus b operating on xb, and since d is it is a linear operator, so d square operating on xb plus a times d operating on xb plus bxb. Now, d square xb, the value of d square xb we can put from here. So, x d square b plus 2 db, and then derivative of x into b can be put from here. So, we have a times x db plus b plus bxb, and which can then be written as x d square b plus a db plus bb plus 2d plus a operating on b. Now, d square b plus a db plus bb is nothing but the operator fd operating on b. So, we have x into the operator fd operating on b, and then 2d plus a can be interpreted as the derivative of fd. In short, 2d plus a can be interpreted as if we have differentiated fd with respect to d. Now, let us suppose that when fd operates on the function v, we get another function say b1. So, that when you apply the inverse operator 1 over fd on this equation, fd v equal to b1, we get v equal to 1 over fd operating on b1. Now, let us put the value of b as 1 over fd operating on b1 in this equation. So, we get fd operating on x into 1 over fd b1 equal to x b1, because fdb is b1. So, x into b1, and then f dash d operating on b is equal to 1 over fd b1. Now we will operate on both sides by 1 over fd. So, we operate on this equation by 1 over fd. Since fd and 1 over fd are inverse to each other, so we shall get on the left hand side only x 1 over fd b1. So, we get x 1 over fd b1, and then the right hand side we get as 1 over fd operating on x b1, then 1 over fd operating on f dash d, and then 1 over fd on b1, which can be interpreted as f dash d over fd whole square operating on b1. So, we get this 1 over fd operating on x b1, then f dash d over fd whole square operating on b1. Now, let us write the value of 1 over fd x b1 from here. So, 1 over fd x b1 is x times 1 over fd operating on b1 minus f dash d over fd whole square operating on b1, and hence 1 over fd operating on x b1 is nothing but x 1 over fd operating on b1, and then this can be interpreted as derivative of 1 over fd with respect to d, like we differentiate 1 over x with respect to x. So, minus f dash d over fd whole square can be interpreted as the derivative of 1 over fd. So, that is operated on b1. Now, let us see how we will apply this formula. Now, here one more thing, this formula can, since b1 is an arbitrary function, b was an arbitrary function, so b1 is also arbitrary. So, we can write this formula for b. So, 1 over fd operating on, so we get the following formula, b1 can be replaced by b. So, 1 over fd operating on x into b gives you x 1 over fd operating on b, and then d over dd operating on 1 over fd operating on b. This is the formula. Now, let us see how we shall apply this formula. So, let us look at the equation d square minus 2d plus 1 by equal to x sin x. So, here let us find particular integral. So, 1 over d square minus 2d plus 1 operating on x sin x. So, this is a second order non-homogeneous linear differential equation where Rx is x is sin x. So, it is of the form x into b where b is sin x. Now, applying this formula 1 over f d x b equal to x times 1 over f d v plus d over d d 1 over f d v, we can write this as x times 1 over d square minus 2d plus 1 sin x, then d over dd of 1 over d square minus 2d plus 1 sin x. This is equal to d square can be replaced by minus a square. So, x times 1 over minus 1 plus 1. So, we get minus 2d, and then we have minus 2d minus 2 upon d square minus 2d plus 1 whole square operating on sin x. The derivative of 1 over d square minus 2d plus 1 with respect to d we have written here. Now, this is equal to 1 over 2d operating on sin x. So, we get minus 1 over 2 x, then 1 over d sin x means integral of sin x, which is minus cos x, and here we replace d square by minus 1 square, that is minus 1. So, minus 1 plus 1 whole square, minus 1 plus 1 means 0. So, we get minus 2d whole square, which is 4d square. So, we get minus 2d minus 2 upon 4 d square can be replaced by minus 1 square. So, we get minus 1 sin x, and this will then be equal to, so we can write x 1 by 2 x cos x, and minus minus becomes plus 2y. So, 1 by 2, and then d minus 1 will operate on sin x, will give you cos x minus sin x. So, this is the particular integral in this case. Now, this formula is generally avoided because of the complicity of this formula. We use alternate method to determine the particular integral in case of the functions where we have x into b. So, let us see alternate method here. So, let us find particular integral. By an alternate method. What we do is we can write it as imaginary part of 1 over d square minus 2d plus 1 operating on x times cos x plus I sin x. X sin x is imaginary part of x times cos x plus I sin x. Now, this is equal to imaginary part of 1 over d square minus 2d plus 1 operating on e to the power I x, because e to the power I x is cos x plus I sin x. Now, let us apply the formula 1 over f d operating on e to the power x into b. So, that formula if we apply, we get this is d minus 1 whole square, d is replaced by d plus I. So, we get d plus I minus 1 whole square operating on x. Let us assume that, let us say I minus 1 is equal to some alpha, if you assume, then this is e to the power I x by alpha square 1 plus d by alpha raised to the power minus 1. Since the power of x is 1 here, when we expand 1 plus dy alpha to the power minus 2, we just retain the power of d as 1, because the d square when operates on x, it will give us 0. So, this is imaginary part of e to the power ix. Alpha square will be equal to I minus 1 whole square, which is I square plus 1 minus 2i. So, this is minus 2i. So, we get e to the power minus ix over minus 2i, and then 1 plus dy alpha minus 2 will give you 1 minus 2 dy alpha. We are not writing higher powers of d operating on x. So, this will be equal to imaginary part of x minus 2 upon alpha. Now, this is equal to imaginary part of cos x plus I sin x divided by minus 2i into x minus 2 upon I minus 1. So, when you simplify this expression, write it as a complex number alpha plus say a plus ib, and then take the imaginary part, you will get half of x cos x plus half of cos x minus sin x. So, we get half of x cos x plus cos x minus sin x. So, this is an alternate method of obtaining the particular integral for functions of the type x into b. Now, let us discuss an application. We had earlier discussed an application in mechanics for the homogeneous, where we had homogeneous linear differential equation of second order. Now, we are doing considering an application where we will have a non-homogeneous linear differential equation of second order. So, let us discuss force oscillations. In the force oscillations, we apply a variable force which we call, we can denote by Ft. T is the time variable. It is called input or the driving force. It is applied to the mechanical system, the mechanical system which we had considered earlier in the case of homogeneous linear differential equation of second order. We had considered a vertical spring and with the fixed support, and then mass m is suspended from the lower end of the spring, and then it is attached to a dash pot. It is attached to a dash pot filled with a viscous liquid. So, the differential equation now, when we apply the variable force Ft, will be of the form m by double dot plus c y dot plus lambda by equal to 0. In the absence of this variable force Ft, we had obtained the second order differential equation homogeneous m by double dot plus c y dot plus lambda by equal to 0. So, now this is second order linear non-homogeneous differential equation. Its solution, it will be called an output or the resonance of the system to the driving force. Now, in the case of this non-homogeneous differential equation, we generally considered periodic driving force because it has a special interest. We have special interest in this. So, let us consider Ft to be equal to f naught cos omega t, where f naught is positive, omega is positive. Then the particular integral, so when you take Ft equal to f naught cos omega t, then particular integral will come out to be a1 cos omega t. We can check it very easily. The particular integral will come out to be a1 cos omega t plus a2 sin omega t, where a1 is equal to this and a2 equal to this, and omega naught is the root lambda by m, the natural frequency. Now, provided the denominator is non-zero, the denominator here, this denominator, if this denominator is non-zero, we get this by pt equal to a1 cos omega t plus a2 sin omega t. Now, the general solution, as we know, the general solution will then be the sum of the complementary function, which is the general solution of the homogeneous linear differential equation, and the particular integral by pt. So, this is the complementary function of the homogeneous equation associated to equation 1. Now, then in the case of free oscillations, we had three cases. when c square is greater than 4 lambda, we had over damping. By t came out to be this, where p was we had taken as c by 2m, q equal to this, and then we had the second case, c square less than 4 m lambda, which was the case of under damping because c is the damping constant. So we had the solution by t equal to c times e to power minus pt cos omega var t minus lambda, and q was equal to I omega var is equal to this. Now in the third case, the critical damping, when c square becomes 4 m lambda, we had by t equal to a plus bt e to the power minus pt. So these are the solutions of the associated homogeneous equation. Now forced oscillations without damping. First we consider the case of forced oscillation without damping, that means the damping constant c is equal to 0, and then the solution will take the form by t equal to c cos omega t minus, we can see it from here, by t equal to by ht plus by pt. By ht plus by pt, we have found by pt as a1 cos omega t plus a2 sin omega t. So in that you put c equal to 0, you get the value of by pt, and by pt comes out to be f naught over m omega naught square minus omega square cos omega t, and when c is 0, c square, if you look at this, c square is 0, then c square will be this will be 0, so 0 will be less than 4 m lambda, and therefore by ht will be equal to c e to the power minus pt cos omega t var t minus delta. So we will get this as c times, because p is equal to 0 here, this p is equal to 0 because c is 0, so we get c times cos omega var t minus delta. So we get by t equal to c cos omega naught t minus delta, and then f naught over m omega naught square minus omega square cos omega t, in the case c equal to 0. Now here this is a superposition of two harmonic oscillations, this is a harmonic oscillation and this is also a harmonic oscillation. So we get a superposition of two harmonic oscillations with frequencies omega naught over 2 pi, here the frequency is omega naught over 2 pi, here the frequency is omega over 2 pi, which comes from the driving force. The amplitude is given by a naught, the amplitude is given by this one, this is the amplitude f naught over m times omega naught square minus omega square. Since lambda by m equal to omega naught square, we have taken omega naught equal to square root lambda by m, or omega naught square equal to lambda by m. So from here if you substitute the value of m in the expression, this one, in the expression f naught over m times omega naught square minus omega square, when you substitute the value of m from the relation, this one omega naught square equal to lambda by m, we get f naught by lambda omega naught square by minus. Now this we can see from here, as omega tends to omega naught, this a naught tends to infinity, so amplitude becomes very large. Hence if the frequency of the periodic driving force omega equals the natural frequency omega naught, the oscillations become too large. So this case is the case of resonance. The differential equation in the case of resonance will then become, if you look at the differential equation, this is our differential equation, we are taking c equal to 0, okay. So m by double dot plus lambda by equal to ft, this equation will then turn into this equation by using the relation omega naught square equal to lambda by m, we can write it as by double dot plus omega naught square by f naught over m cos omega naught t, and its general solution is then by t equal to c cos omega naught t minus delta f naught t sin omega naught t over m omega naught. We know how to determine the solution of the differential equation. Particular integral here will be 1 over d square plus omega naught square operating on cos omega naught t, and we know the formula for that. So we can make use of that formula, 1 over d square plus c square operating on cos cx. We have cos omega naught, yeah, cos cx, that we have found as x sin cx divided by 2c. So we make use of this formula to get the particular integral, this one, f naught t sin omega naught t over 2 omega naught. Now forced oscillations with damping. So here in this case c will be positive, and from the equations 2 to 4, let us look at the equations 2 to 4 here. So in this case, when damping is present, then there arise three cases. corresponding to the discriminant c square greater than 4m lambda, c square less than 4m lambda, then c square equal to 4m lambda. In all the three cases you can see that by t tends to 0, because when q is less than p, q is 1 by 2m under root c square minus 4m lambda, so q is less than p, so this p minus q is positive. So when t tends to infinity, this goes to 0, this also goes to 0, and here when t goes to infinity, e power minus pt goes to 0, and cos omega over t minus delta is bounded, so this is tending to 0, and here also when t tends to infinity, because of the exponential function, by t goes to 0. So now the by t there is nothing but the complementary function, because by t is the general solution of the associated homogeneous linear differential equation. So by t is by h t, so by h t goes to 0 as t goes to infinity. Hence after a sufficiently long time, the response to the sinusoidal input is given by pt, because by h t term tends to 0, so by t is nothing but by pt. This is known as the steady state solution. In this case, the oscillations of the output have approximately the same frequency as that of the sinusoidal input after a lapse of sufficient time. So with this I will close this lecture. Thanks.